Get ready to blast off into the incredible world of brain-computer interfaces. Neurocareers Doing the Impossible is taking you on a journey to meet the fearless pioneers pushing the boundaries of what's possible. In this special series, we'll be shining a spotlight on the nominees and winners of the International BCI Award, one of the biggest and most prestigious awards in the BCI world. You'll hear from BCI professionals as they share their revolutionary work and get a behind-the-scenes sneak peek at what it takes to be a winner. So, buckle up, grab a snack, and get ready to be amazed as we explore the impossible becoming a reality in the world of BCIs. But before we blast off, I want to give a big thanks to the co-host of this BCI Award edition on our podcast, Dr. Christoph Guger and GTech Medical Engineering. When I was a faculty member at the University of Cincinnati and Cincinnati Children's Hospital Medical Center, my team and I did some pretty amazing stuff for patients needing epilepsy surgery. We would put special sensors, also called grids, directly on their brain to prepare for surgery and create maps of their brain in a much faster and safer way than is usually done. It's called high gamma mapping, and it lets us figure out in just a few minutes the essential parts of the brain that need to be spared during surgery. Can you imagine? You can create a map of language, motor, and even math processing in no time. It was the first time this innovative technology was used at Cincinnati Children's Hospital Medical Center. When I moved to Florida, I established the first functional brain mapping and BCI program at Florida Hospital. I continue to use high gamma mapping to help epilepsy patients avoid losing their ability to speak or move after surgery. But even cooler than that, I created brain-computer interface studies that let patients control things with their brain in real time. Our patients could even spell words with incredible speed by just using their brains. No hands involved. I also discovered that brain-computer interfaces could help patients move their chronically impaired hands or legs years after a stroke when not much else could help them. So, I started working with the faculty from Advent Health University to help these patients restore their ability to use their hands. I received special training for it, and it's still mind-blowing how cool it is. My favorite part of what I do is teaching. At my established Institute of Neuroapproaches, I've integrated all my experience and knowledge into a unique course on brain-computer interfaces. With graduate neurobiology students, we started with theory, and then I gave them the BCI equipment so they could have hands-on experience working with BCIs. It significantly improved the way students learn, and they absolutely love this practical part of learning how to use neurotechnology. And all of this was made possible thanks to GTech's awesome brain-computer interface technology. They have everything from high-tech up to 1024-channel EEG systems to wearables, tools for neurorehabilitation, such as the medical-grade system recoveries and educational kits with unicorn hybrid plug for learning how to work with BCI technology. But the most important part is their support and care. I have enjoyed working and collaborating with Dr. Christoph Guger and GTEC employees for over 15 years, and I hope for many more successful years ahead. So, if you are interested in GTEC's brain-computer interfaces and neurotechnologies, check out their website at gtech.at. It's worth it. And keep in mind, I do not receive any financial support from GTEC and share my honest opinion supported by many years of experience working with their equipment. Dear listeners, welcome to another exciting episode of the BCI Award Neurocareers podcast series, where we explore the incredible journeys of neuroscience and neurotechnology professionals. In today's episode, we have the privilege of diving into the world of Dr. Courtnie Paschall. Courtnie is a researcher, mentor, veteran, team builder, dreamer, and doer with a passion for pushing the boundaries of neurohaptics, virtual reality, and brain-computer interfaces. A project in virtualis, and Intracortical Neurohaptic Interface in virtual reality by Dr. Paschall and her team was nominated for the International Annual BCI Award in 2022. During her PhD, Courtnie embarked on groundbreaking research, building novel virtual reality experiences for individuals with neural devices. Her work enabled revolutionary cognitive neuroscience research and the development of brain-computer interfaces. Notably, Courtnie constructed the world's first bidirectional VR BCI integrated with intracranial electrodes, allowing individuals to control a VR avatar with their thoughts and even feel virtual objects through innovative neurohaptic technology. Courtnie's dedication to meaningful innovation and personal success extends beyond her research endeavors. She continues to mentor graduate, undergraduate, and high school neurotech researchers and remains actively involved in the neurotech student group, which she co-founded at the University of Washington. Join us as we delve into Courtnie Paschall's remarkable achievements, her inspiring journey, and her unwavering belief in the potential of every individual to make a difference in the world of neurotechnology and beyond. Get ready to be captivated by her passion and groundbreaking contributions. Welcome, Courtnie. It's a great pleasure to have you today on our podcast. Thank you so much for coming. Can you briefly introduce yourself and also tell our listeners where you are joining us from?
Milena, thank you. That is such a kind introduction and thorough. I don't have much to add. So I am joining you today from a study in my grandmother's house out in California. I'm just back from a bit of an extended stay out in Indonesia with a, we'll say, Web3 technology group, and en route later this week to the augmentation residency, which is a live-in hackathon being hosted in San Francisco by a kind of combined Harvard, Stanford, and other university group. Yeah. So hi, always en route to something.
Yeah, that is absolutely amazing. Thank you very much for this introduction. And we would like definitely to learn more about all those routes that you are doing. And we will definitely touch upon that in our podcast. Now, I would like to ask you first to introduce the project that you submitted that was nominated for International BCI Award in 2022. And it's a really, really very interesting approach that you took. You're talking about bidirectional BCI. So can you tell our listeners about that project?
Yes, of course. So the project that I submitted to the International BCI Award was the development of a novel brain-computer interface platform. I brought a kind of an integrated virtual reality system into the hospital to work with a specific patient population that receives implants to record brain activity in order to localize seizures. So this patient population undergoes implantation of dozens of individual kind of electrode probes to give me hundreds of electrodes worth of coverage of the brain. They are in a hospital bed undergoing chronic neural recording, so continuous recording of neural activity for about a week. In that population, normally studies are run on laptops or with behavioral setups. What I was able to do was integrate a fully immersive virtual reality system with integrated eye tracking, 3D sound, and connect that to both the neural recordings and the option of direct brain stimulation for neural feedback. With that system, I built a novel neurohaptic interface, a word that I kind of have recoined from the literature. Neurohaptic, in this case, refers to the delivery of haptic information through direct brain stimulation. So essentially, I built an immersive virtual reality experiment in which a patient sitting in a hospital bed could reach out and interact with a virtual object within a virtual environment and then receive information about that object. In this case, a kind of synthetic version of touch. I was able, because of the flexibility of the virtual reality system, to introduce novel ways of delivering that touch sensation and connect it to first person, we'll say, self-initiated naturalistic activity. What I mean by that is in virtual reality, you put a headset on, you can see your hands equivalently in the virtual environment. You can watch yourself reach out in a way that matches all of your proprioceptive sense and information to see an object that you can interact with, that behaves visually as you would expect an object to, but that in real life doesn't exist and you can't feel. That experimental setup, impossible outside of VR, allowed me to pursue neurohaptic sensory information in a way much more analogous to real world touch. And then I didn't actually submit this final piece to the International BCI Award because it hadn't been completed by the time the award submission was due, but I was able to close the loop. And instead of having the human reach out with their own hand to complete this object interaction in virtual reality, I was able to, in real time, decode neural signals to trigger that interaction, making the first closed loop or bidirectional virtual reality or extended reality brain-computer interface, which you could call like a prototype of the Matrix if you wanted to go sci-fi.
I absolutely love sci-fi, and I'm sure many of our listeners as well. Yes, yes. That's absolutely amazing. Thank you very much for this introduction. The project looks so interesting, and I would like to go into various details of it. But before we do that, I would like to start with the history of the project. And by history, I mean, how did you get to that place where you were able to do this project? How did it all start? And if you can guide us through your career that led to this place where you are now, because I think your career is very extraordinary. It's not a very common type of career. So
extraordinary in the kind of winding long route of it. I appreciate that. So I will say I began my academic career as an applied physicist studying nuclear physics and we'll say kind of applied electromagnetic experimental physics at the U.S. Naval Academy. I enjoyed at that time tinkering with we'll say the fundamental matter of reality. I think what drew me to physics originally was that question, what is all of this? Why does it work? What are the underlying equations that govern reality? And that question, what is reality, I think traces very neatly through the rest of my academic career. So from the academy, I graduated, served as a naval officer, had the opportunity to study to become a helicopter pilot, left that career to travel the world, I would say, have my hippie vagabond experience, which I guess in some ways is a pursuit of reality through maybe mindfulness, contemplation, meditation, and seeing the world as such, and felt in the midst of all of that, this call back to research and academia. I ended up going back to school through the University of Colorado Boulder to complete pre-medical courses, and in the same time had the option of a second degree. So while completing the pre-medical requirements to give me kind of a new option and direction, I also studied formally neuroscience and electrical engineering. And it was in the process of completing this degree that one of my professors and mentors asked if I was applying to MD PhD programs. I didn't know that those existed, and it was a pretty pivotal conversation for me to realize that these seemingly disparate paths that I was pursuing, this interest in research and we'll say fundamental science, this burgeoning curiosity about the brain, which is another way that one can study reality, since as a human, my consciousness is filtered through the brain, if nothing else, with this desire to have maybe a bit more of an immediate impact in people's lives that you have the opportunity to have as a physician. So combining those two degrees, I applied to MD PhD programs across the country, had many options, and ended up selecting the MSTP, Medical Scientist Training Program, with the University of Washington, Seattle, because of their neurotechnology focus and institute. There was the Center for Neurotechnology at the time, an NSF-funded center at the University of Washington, which was a kind of multi-school research institute focused in Washington, but combining the research efforts of MIT, a number of other technology institutes, and UW. In or through this institute, I found the lab of Jeffrey Ogeman, Dr. Ogeman, a practicing neurosurgeon and scientist, and Dr. Rajesh Rao. And that lab had a specialty in working with patients with the implants that I described earlier, and a history in synthetic touch development and brain-computer interface. So this kind of winding path from, a kind of a pure mathematical approach to reality through physics into a bit more of a wandering approach about the world into maybe inevitably neuroscience and electrical engineering, the question of the substrate of consciousness through biology and the ways that we can interact with that through implanted devices landed me in exactly the right lab in which to begin really exploring these questions. So the specific origin, I would say, of the virtual reality side of this was both those underlying questions of the nature of everything and the advance of hardware and technology. The research that I completed really couldn't have been done a decade ago. It required that the virtual reality headsets become accurate enough and sensitive enough to translating real world activity into the virtual space that I could bring them into the hospital and very safely and very accurately conduct the kind of research that I did. I say it's probably the origin story in chunk.
Yes, I love the story. It's really very inspiring. Also, you show that main question which you are bringing with you through all the stages of your lives, all the stages of your career, trying to understand, yes, the nature of everything, what is our reality, yes, and answer it in different ways, yes, by different means. So, which is absolutely beautiful. And we will talk a little bit more about that as well. Now, your project, how did it start? Even for the students who are starting their research, the idea, yes, how did you generate that particular idea? What did it take for you to start this project? So, which is usually the most difficult part, yes, to start, to have all the pieces together and start it. So, if you can guide us through that.
Certainly. So, in many ways, the virtual reality BCI project started a little over halfway through the full PhD. So in addition, I would say, to the challenge of getting started, I also had a global pandemic arrive at year 2, year 3, essentially. And it was in that pandemic, though, that an opportunity popped up. The University of Washington also hosts the UW Reality Lab, and they put a call out for a kind of a seed grant opportunity for novel uses of virtual reality. At the time, I was studying neural signals analysis for closed loop deep brain stimulation. I was exploring, we didn't call it neurohaptics at the time, but direct cortical stimulation for this artificial touch. Prior work from a grad student, Geneva Cronin, was evaluating kind of the specific ways you could change stimulation to make a noticeable difference in the touch that a person felt. And I can dive into what this direct cortical stimulation process really looks like in kind of probably a future question. But this call came out, and that really was the impetus to formalize what I wanted. And it felt very kind of pie in the sky and daydreamy at the time, what I wanted to do if money were no object, as a research side question. And I pitched to my lab, my PIs, and a new professor that had since joined the lab, Jeffrey Heron, a proposal for an embodiment experiment. The idea was to recreate the classic rubber hand illusion in virtual reality in a way that hadn't been done before. There had been attempts to recast this RHI experiment in VR, but they were very rigid and stereotyped and limited by the technology and the software for virtual reality interface at the time. But the technology had gotten so much better, and the software, I worked in Unity, the software had also become so much more flexible and easy to work with as an experimenter. I felt we could redo this existing work to really get a sense of the neural correlates of embodiment, and to begin to comment on how to make both neural prosthetics feel more real to the person using them, and embodiment in a VR sense for the future of gaming and, we'll say, extended reality and augmented reality technologies. That proposal also built on existing work that the lab had done with actual rubber hands placed next to a person. I wonder if I should double back, though, and define what the rubber hand illusion is.
Yes, maybe. Yeah, not everybody might be familiar with it, although I'm sure many people, but we still may have new students who are just getting into the field.
Of course. So the rubber hand illusion is very well named. The original experiment done in the 90s used a literal rubber hand placed next to a person's real hand or at some distance away from their real hand. And then their real hand was covered from view, often done with like a screen and a towel. Then the experiment proceeds to touch both the rubber hand that the person can see and their real hand that they can't see at the same time. What happens is that the brain seems to associate the touch it can feel with the touch it can see, and it transfers its sense of ownership of hand to the rubber hand. This sense is called embodiment. What maybe hilariously is done next, if you look this up on a YouTube video, is that the experimenter could pull out a hammer and threaten the rubber hand, and the person will flinch and pull their real hand away, even though their real hand was not in danger. In a more scientific way of evaluating this rubber hand illusion, there's also an effect known as proprioceptive drift. And what that is, if you ask the person to point to their real hand, instead of them pointing to their real hand, they'll point to the rubber hand as the hand that's theirs. And the amount to which they drift from their real hand towards the rubber hand is called proprioceptive drift. We found actually results that are in the process of being published, that the transfer in virtual reality, this proprioceptive drift, was extremely strong and seemed to be much, that the virtual reality was incredibly persuasive. We also, and it was so interesting to see this, found that even if you tell the person where their hand really is, they will still experience proprioceptive drift. That is fascinating, that the brain is willing to create, we'll say, alternate realities in which the information it sees and feels, this concept of sensory integration, it will hold as truth. My guess is it holds that information contingently, meaning the brain is very capable of creating alternate cognitive spaces in which new rules are true. I would say that aligns with other behavior I saw in virtual reality. For example, in VR, physics does not rule. In fact, as an experimenter, I can decide what the global physics of any particular space or object is. So if I have a subject reach out and grab a block in a virtual reality setting and grab a virtual block, I can choose as the experimenter if that block responds to gravity. Maybe that block floats. Maybe that block flies out of their hand ballistically. All of those realities and probabilities can be coded by the researcher in VR. And what I found is that as long as I was consistent, whatever I coded a block to do, the brain rapidly adjusted to. If the block had no gravity, no problem. Gravity doesn't exist here. If the block would fly ballistically from a user's hand, no problem. Blocks have their own velocity and energy source here. The brain would hold these contingent realities rapidly and easily, and yet never really had a difficulty transitioning back to the strong prior of real world physics. That's a fun, interesting research direction that we began to touch on with this rubber hand illusion and some of the innovations we were able to introduce through our virtual implementation of RHI. And also what I'm hoping the real use of this virtual reality platform is for my and other labs. The ability to control underlying probabilities, to answer questions about the way the brain forms expectations, for example, is ready and available in VR in a way that's impossible to control in the real world.
Thank you very much, Courtnie. It's very, very exciting. All those possibilities that this research is really showing to us. And now I would like to start with all the stages of your research, starting with your participants. Yes, you already told our listeners that these are usually people who are undergoing evaluation for epilepsy surgery, and they have a particular coverage with the electrodes positioned directly on their brain. So how did you choose, which electrodes, which coverage will you use or you will not use? What were particularly you are looking for in those electrodes?
Yes, great question. So to paint that picture a little bit, I worked largely with children in a children's hospital. So we'll say ages 7 to mid 20s who were receiving electrodes in order to map the origin of their seizures, which we've covered before. What's wonderful and unique about working with a children population or a younger population is the kind of coverage due to the types of seizures that you're more likely to see in kind of non-adults or non-trauma based epilepsy situations, as well as the openness to donning a VR headset. It turned out that our adult patients at another hospital sometimes had to be convinced to play the virtual reality game, but a children's population was so eager to put the headset on, which was fantastic. These patients, whether children or adult, are receiving ECOG or electrocorticography arrays, which are typically flat grids of electrodes, grids or strips that lay along the surface or the cortex of the brain. This gives us broad coverage for recording across different cortical surfaces and the ability to directly stimulate the kind of outermost surface of the brain. Often we would get coverage over the sensory cortex and or the primary motor cortex. Either of those kind of regions around the central sulcus can be stimulated to elicit an effect or a percept that the subject can identify. If I stimulate the sensory cortex over the hand area, for example, then in the body on the contralateral, so the other side of the body, hand, the person can feel something. Traditionally, that feeling can be pointed to, so it can be localized, and it can be localized reliably, but the sensation that's elicited doesn't feel real. It was often described as being maybe electric, but not really. There's one kind of highlighted subject who described the sensation as wind moving over their hand, kind of. And that one was published frequently because it at least alluded to something natural, when most of the time these elicited sensations felt very unnatural and difficult to describe. So one of my goals was to see if we could make that sensation from directly stimulating the sensory cortex a bit more natural. If you kind of wind back a little bit, if you stimulate the motor cortex, you can elicit sometimes a twitch or the feeling that somebody is about to move. And either of those can again be identified by the subject and as such are useful as feedback. But in my work, I tried to focus on the sensory effect whenever possible, and that was dependent on coverage. To wind back even further, in addition to these electrocorticography or flat grid arrays, I also worked with stereo EEG, which I describe a bit as more like flexible coffee straws that are slowly tunneled to deep brain structures with electrodes embedded along the length of that probe. Those electrodes don't tend to give very good cortical coverage. Maybe one or two electrodes might listen from or be able to stimulate cortical tissue, but it does give a kind of column, a depth recording in brain tissue. Most children's patients now receive both ECOG and stereo EEG. Most adult patients receive only stereo EEG. We're seeing fewer and fewer electrocorticography patients in the populations that I saw anyways in Seattle. My work was able to demonstrate not only that, virtual reality setups and apparatus do not perturb the neural signals that are being recorded from either electrocorticography or stereo EEG arrays, was able to demonstrate that the headset is comfortable for these post-operative patients, whether they receive stereo EEG, which in some ways is a less invasive, or we'll say maybe less traumatic brain surgery, compared to electrocorticography, which requires a craniotomy, which requires that a portion of the cranium is lifted off of the brain in order for the electrodes to be implanted. Even if patients underwent fairly extensive surgeries, the headset was very comfortable and worn by every subject that I had the opportunity to work with for an hour or more, and often with the request of additional games or experiments if it was available. Additionally, the work that I completed was able to demonstrate the ability to use either electrocorticography, surface grids, or these depth stereo EEG probes to both decode the intent to move or the desire to complete an action in virtual reality and deliver meaningful sensory feedback through direct stimulation. Stereo EEG had been used to demonstrate this before, but really in a very limited way. And I don't know if it's leading the question too much, but I would love to talk about the new way that I used to deliver this sensory information that made the very limited cortical coverage of stereo EEG more than enough.
Yes, I definitely would like you to talk about that and maybe to give our listeners a perspective. Yes, that in United States, the epoch electrocorticography was used for a very long time, whereas in Europe, people used more stereo EEG. So now that stereo EEG started to come here, and there are combined recordings of one and another, but still we need to adjust to this new recording of stereo EEG here. And the parameters of stimulation via those depth electrodes in stereo EEG, they're really not very explored. The signal by itself is also not really explored. And here, really, if we establish that baseline and understand what you did really looks very powerful. It's a really big accomplishment, and to be able to record, get the meaningful information, and to find right parameters to stimulate, which are very different from what we used to do, stimulation via echoic electrodes. So if you can give that perspective and then, tell exactly what you did to get that meaningful stimulation and also decode the response that you are interested in from both kind of electrodes.
Perfect. Yes. So I'll start with the kind of statement of finding the precise stimulation parameters. So traditionally, direct cortical stimulation or direct neural stimulation is delivered as square wave pulses. So these are kind of digital in many ways, as much of an analog stimulation can be digital, kind of on, negative, on, and off stimulation pulses. So there's some set amplitude for some duration, and then that amplitude inverts and you drive the negative current amplitude, and then you go back to zero. So square wave, up, down, biphasic, charge match stimulation pulses. And experiments around the sensory effect of these pulses tended to focus on how much you needed to modulate each parameter to have a noticeable difference in the output stimulation. So that would be at a particular set of electrodes that would drive current through the sensory cortex. If you stimulated at a sufficient amplitude for a minimum amount of time, where was that effect felt and what did it feel like? And then if you change that amplitude to make it higher, was that enough to change the sensation? And changes in sensation were typically evaluated as magnitude. That was a a weird feeling I barely felt, or a weird feeling I could really feel. And then if the change was big enough, the subject could reliably tell you the one that he or she barely felt versus the one that he or she really felt. So the traditional structure of this sensory information and direct kind of neural stimulation experiment was, we'll say, fairly limited in some sense. There are only so many parameters that you can shift to get a change in magnitude in the perception. You can change the amplitude, you can change how long you're delivering that amplitude, but there's very strict safety precautions, so you can't change those very much. You can change the duration for which you deliver the individual pulses. So maybe instead of delivering 5 pulses in a particular amount of time, you deliver 10 pulses and double that amount of time. You can also change the frequency within that first time block, but that didn't show a lot of effect for changing magnitude. Something that had been done in monkeys previously was to introduce a kind of block frequency component. So now, instead of delivering one 1 second series of pulses or delivering pulses for 1 second, you would instead deliver pulses for 1 second every second or every 2 seconds, or 1 second of pulses every 10 seconds. And that was the level of kind of modulation that had been researched prior. What I was able to do in this patient population, and in some ways because of the virtual reality platform, was to design and introduce stimulation that changed in amplitude every there had been an open question in the field if imitating through these square wave pulses a continuous neural signal would better replicate the way the brain expresses natural touch. What I was able to demonstrate is some increase in naturalistic understanding of stimulation. So, for example, if I delivered a stimulation sequence that kind of moved, I called it ziggurat, so like a pyramid, right? It moved up to a peak amplitude and then back down in a series of pulses, and then back up and then back down. If I contrasted that with stimulation that moved up and down faster, right? So this continuous stimulation with a different temporal structure over time, the subject innately could tell those apart. One was bumpy, one was less bumpy. That translation of interpreting stimulation into naturalistic kind of descriptors was one very exciting, and I think suggests that this really is a good avenue for crafting complex sensory information as feedback back to the brain. This avenue being continuous temporal or amplitude modulation of the stimulus series. I would also love to have had the time to explore, and maybe some future lab will, focusing on frequency modulation, so AM versus FM in the stimulation delivery. So this work demonstrated, yes, there's more naturalistic understanding, but more importantly, that design space was intrinsically understood by the user or by the subject, meaning the brain kept a temporal track of the stimulation being delivered. And it built through these individual pulses a complex understanding of the way the stimulation was changing in time that hadn't entirely been explored before. And this complex architecture of stimulation had not been done in humans or animals, actually, because I will say one of the challenges in an animal study is you can't ask the animal to tell you how this feels. But in a human study, you can ask, what did that feel like? How did that one feel different, if it felt different at all? How would you describe that? Which of these, fits this situation better? Humans are fully conversant. Also, one of the beauties of getting to work with this patient population, where we had a week to build a relationship and to build an understanding of these virtual environments and the neurohaptic interface or the bidirectional brain-computer interface when we got there. Does that paint a picture?
Yes, absolutely, absolutely. And you describe how before people were talking about their experience with the somatosensory stimulation of the brain. And you described it as the wind blew, yes, through their hand. So, what were their experiences in your type of stimulation? What did they report? How did they describe it?
So, it varies fairly broadly depending on where along the sensory or motor cortex you're stimulating. And I think, and future experiments will prove this, in virtual reality, you can deliver visually suggestive information. For example, you can make it look like an object might be on fire, right? You can make an object look bumpy or look smooth, look square, look spherical, I guess cubical or spherical. That, I think, we will find has a very strong impact on the interpretation of these very artificial sensory stimuli that are being delivered to the brain. That said, my kind of structure of the experiment, I started by delivering these different temporal patterns and asking for, we'll say, naive and innate interpretations. What does this one feel like with no visual information and the headset not on? So in that context, the descriptions included things like bumpy versus smooth. One's bumpy, the other one's bumpier, which makes sense given the architecture of this kind of square pyramidal set. I also delivered something a bit noisier, didn't have a clear repeated sequence, and had a much higher frequency of we'll say, peaks and changes. And interestingly enough, that stimulation sequence tended to elicit extended perceptual effects, meaning if I delivered this noise stimulation for a quarter of a second, the perceptual effect would linger. So the descriptors were a bit more naturalistic, bumpy, smooth. I'm trying to think of others. Descriptions of a sense of something moving with a particular frequency or not really moving at all or kind of holding constant, so that ability to reframe the temporal structure seemed to be constant in the types of responses I was getting. Interpretations of that as tactile depended on where in the brain I was stimulating. If it was closer to the motor cortex, it might be described as kind of an awareness of a pulsation, but without actual physical movement. There were a few other descriptors, but I think, again, in the context of there being no support for interpretation, just receiving a novel stimulus and interpreting it, the conclusion that I saw from the data that I collected was an awareness of temporal structure that mimicked things with temporal regularity in the real world, rough and smooth, as an example. Within the context of the virtual reality setting with this stimulation, by having introduced real haptic, so controller buzzing feedback, I saw the language shift to representing the direct brain stimulation also as if it were a buzzing haptic interface. So I think similar to the kind of contextual flexibility that we demonstrated in the virtual reality rubber hand illusion, the brain is very willing to assign value or labels to novel or unexpected information. And we have, within the virtual reality context for future neurohaptic experiments, the opportunity to specifically explore the flexible assignment of value to these stimulation sequences based what's happening in the VR setting. I did have one subject describe a certain type of stimulation as warm, which was very cool and unexpected. And I had already introduced the idea of one of the virtual objects being lava and one of the virtual objects being ice. So I'm wondering if I planted the idea of temperature differentiation and the brain was very willing to take a sensory cortex direct brain stimulation sequence and call it warm.
Yeah, that's amazing. How much can we learn about our brain by using this approach? That's absolutely astonishing. I'm very curious if you found any difference in how people perceive the stimulation that was provided by electrodes on the surface of the brain, electrocardiographic electrodes, or those stereo EEG depth electrodes. Did you notice any difference?
I would say I can't answer that, but I think the question deserves to be answered. So if anybody's listening and is curious about pursuing that specific research question, I don't know the answer. I focused on the differentiability, telling one stimulation sequence apart from another, and the usability. If you can differentiate, can you then make a different behavioral decision based on that information? Within the context of the experiment I built, that would be throwing a virtual object. So you reach out, you grab an object, you receive a distinct type of stimulation. If you can differentiate what that sequence is, you would throw it towards a different target. And so it was a kind of a sensory categorization or distinguishing differentiation task. Within that, I didn't ask or shift between stereo EEG and ECOG at the same location in the brain because I didn't have the ability to do that. But I think it would be a very interesting question. One of the, I think, potential conclusions or highlights in being able to demonstrate the usability of stereo EEG for both decoding, which I haven't really talked about yet, and encoding the sensory information is that stereo EEG, analogous to deep brain stimulators, both depth probes, has a very robust history of safety in chronic implant for patients. And as a result, stereo EEG might be a more functional way forward for kind of real world brain computer interface implants, in the sense that there's been a lot of development around cortical arrays that haven't yet translated to an ambulatory population. But stereo EEG, deep brain stimulators, have been in ambulatory populations for going on decades now. I don't know if that's too jargon heavy. I think stereo EEG are an important technology or implant, we'll say, to consider for brain-computer interface moving forward, as opposed to minute cortical arrays.
Yes, yeah, I think that's a very interesting question to explore because as we're going towards those implantable brain-computer interfaces, neuroprosthesis, that question will emerge a lot. Now I know that there are at least two directions. One is using actually ECOG-like electrodes that are placed on the surface of the brain. And this is one of the project that was nominated for BCI Award. It's for speech prosthesis typing. So because of the large distribution of language areas, they're trying to use those large grids of electrodes, and they're showing that it's viable. But other systems, they are using penetrating electrodes, like we're talking about depth electrodes. Those are still penetrating that are being used, Utah array, for example, and what Elon Musk is proposing is they're still penetrating. So those would be not schematics, but at least more like the depth electrodes that you're talking about. Just there are many, many, many of them, thousands of them. And the question is, a student actually who asked this question, and I thought, it's really relevant to what we're talking about how can you really stimulate anything with those thousands and thousands tiny, teeny electrodes that are so near each other, that are so close. How can we do it? How that is even possible? So I don't know if you have something to say about that as well.
So one of the things at the lab that I had access to was also with the kind of Ogeman and Rao lab that I was a part of, the neural systems lab at the University of Washington, was also a Benke-Fried style of electrode, which is a stereo EEG, so that kind of standard longitudinal probe flexible coffee straw, as I called it, and flexible coffee straw. And this is particular apt because Benke-Fried electrodes are also hollow down the center, and you can kind of insert through them microwires, which fan out at the bottom to give you, 8 or 9 individual wires of local multi or single unit recordings. So it's this combination between stereo EEG and fine single unit neural activity. You can theoretically stimulate through those to look at the way that pico really, but very, very small stimulation currents affect local activity. The challenge with stimulating from these kind of microwire arrays or single unit penetrating arrays, these very, very fine, high impedance electrodes, is the electrochemical interface with the brain. I think maintaining that high impedance fidelity for both stimulation and recording. Perhaps there's a challenge in current kind of spread, or not necessarily arcing, but we'll say electrochemical bridging between neighboring electrodes. I would imagine you would also have the challenge of tissue distribution. The brain is fundamentally electrochemical, so your applied electric current doesn't seem to go very far in an effective sense. There can be, volume and tissue conduction, and this has been modeled. I was actually on a team collaborating specifically to model this purportedly only resistive, potentially slightly capacitive electrical field conduction in the brain, and ways we could leverage that with the known architecture of the brain to steer current between electrode arrays. That work was recently published. I believe Kurt Weaver may have been one of the first authors in that study, collaboration between the University of Washington, a group out of Utah, and the Mayo Clinic. So the question of the best ways to deliver current with the various probe architectures is a wonderful, meaningful, kind of actively researched question. I know of stimulation studies through micro ECOG arrays, but these are not micro in the single unit sense. They're just a much tighter array of tiny visible, large population affecting electrodes. It'll be curious to see how the single unit or small local field potential focused arrays explore sensory feedback. Benefits of the large arrays is this literature history of direct cortical stimulation for sensory feedback. There's a lot of work being done as well using intact peripheral sensation. So maybe one of the ways forward for the microarray BCI approaches is to focus on what's remaining in terms of sensation and not bypass the peripheral system directly to the brain. I look forward to seeing how BCI research combines the strengths of various approaches. I think, biased, of course, the direct delivery of sensory information to the brain will be an important consideration in BCI, not purely for the option of delivering, novel sensory information, be that touch that you can't feel because of amputation, for example, or paralysis, but also extrasensory information. Very common and delightful BCI project is to deliver an awareness of magnetic field strength directly to the brain. I look forward to pure brain-computer interface development that is an ongoing conversation between neural activity and an external memory device, for example. That, I believe, will require something more direct and faster than peripheral touch manipulation. So I think all avenues of research I'm a fan of. I would love to continue to see this direct brain stimulation approach be worked on because I see the application beyond neurohaptics, although neurohaptics is very, very exciting and has the potential to teach us a lot, not only about the ways we can use brain-computer interface for neurohaptic information delivery, but how the brain works with predictable stimuli in a way that we can very precisely control.
Yeah, thank you so much. You already mentioned so many areas of potential research that I think, half of our listeners already have their topics to explore if they would like to. Thank you so much. And you already mentioned that, yes, we talked about the stimulation, but we didn't talk about the decoding of the information that you were receiving. So what insights did you get after using this unique type of stimulation and also recording from the brain areas that were involved in that?
Yes, the decoding side. So I worked, as we've talked about, with a patient population that had typically about a week in a hospital bed undergoing continuous recording. A week is not a long time with which to learn to control a BCI. So one of the refinements, I will say, I made it to this virtual reality bidirectional brain-computer interface that I built was to focus on decoding that would be easy or theoretically easy for the subject to accomplish. What I did was build a pipeline where, based on where the electrodes were implanted, I would have a good guess as to what types of activity I might be able to see. So that could be, I had motor coverage that was in the area of like the shoulder and the upper arm on the right side. And so in this protocol, I would collect 30 seconds of continuous activity labeled with what it was. That could be, rolling the shoulder or moving the elbow. It could be imagining certain things. It could be moving someone's, mouth, for example, or in contrast, moving the left thumb. And in these collected blocks of continuous activity, 30 seconds in each block, no duplicates, that gave me just enough information and enough of a breadth of potential behavioral spreads that I could build or kind of identify potential single decoding options. For example, when someone moves or imagines moving a particular part of their body, the whole brain is responding, but I can identify activity around the motor cortex that is somatically representing of that area. And that activity can often be identified as changes in the spectral components or the frequency of activity, the power distribution in that part of the brain for the all kind of activity of a large neural population. By looking at the spectral or frequency power-based distribution of activity across all of these 30-second epochs, and by across all of them, I mean looking at like a spectrogram. So looking at the power frequency activity and every second of activity across this behavioral data site, this behavioral data set, I can identify frequencies of activity that are most descriptive of a specific type of activity, and I can identify locations in the brain that best represent this particular behavioral action. By automating that pipeline, I would get a ranked set of potential control features. I would pick the top one or two to explore in vivo with the patient. And once there was sufficient, we'll say, understanding of a behavior that would trigger the neural decoder, which typically took about 20 minutes to identify and control, I could then don the headset and begin the bidirectional BCI experiment. I was able to complete this process in one subject. So unfortunately, just one. But in that one, demonstrated two subjects for the pipeline, but only one I had the opportunity to go back into the hospital to complete the full bidirectional BCI loop. So the pipeline, extremely useful, easy to implement. Code is available on request and online. The connecting of these neural triggers to the virtual reality environment completed in one subject. And what I was able to demonstrate surprised me, but again, only in one patient. So I look forward to having the opportunity to continue this line of research, was that the first few uses of the decoding aspect of the brain-computer interface took upwards of 10 seconds to find the trigger. Even though the trigger was known, it was a certain type of movement, directing the brain to accomplish that specific power band increase. I would also, to ensure that there wasn't accidental triggering, I increased the demand on the brain in that particular power band. So the brain had to exceed normal activity in order to reach the trigger. So the first couple trials took around or upwards of 10 seconds. And then once the brain knew what the trigger was, and again, I'm dealing with humans, so I can verbalize, right? Feedback about brain activity. I could tell the human operating their brain in this context what the goals were. And after 3 trials, the time to trigger dropped first below 10 seconds reliably. And in the last 5 trials, all of them were completed in time to trigger below 1 second. The speed of learning in something as simple as a half-dimensional trigger was remarkable and extremely unexpected. And I think with further research would be due to both the real kind of the believable analog, right? They're in a first-person human setting. They're seeing their hand that they just told to go grab an object, go and do that. But then also, when they grabbed that object, received direct neural stimulation, which this subject asked me at some point, when I feel that, is that because I did it right? Which means that the brain was interpreting that contact as success, which is, hijacking the way the brain learns to do something. And the learning rate for using this, again, half-dimensional control BCI, was shocking. And a future publication will show you the graph, but it is a very strong and steep movement toward kind of the delay in time from intent to trigger basically zeroed out and became as fast as the real-time digital signal processors could decode. That was very cool to see. And I would love to, again, in future studies, explore once one trigger is learned, can I layer triggers at a particular electrode? And then with one, trigger learned that quickly, can we add 2 or 3? And at the point of, even 2 triggers, whether left at half dimension or full dimension of control, and I can get into the details of those 2, it's not entirely important, within the virtual reality environment, really even with one trigger, which you can consider a mouse click, I can build sophisticated agents to understand what's happening in the VR setting, to interpret that user's single click in a context and maybe other physiologic signal, eye tracking, for example, in a context-dependent way to evoke very complex behavioral activity. What I mean by that is I had the subjects look at various objects to select them and then use this neural trigger to initiate basically an animation to reach out and interact with that object. through just eye gaze and a single mouse click with the brain, multiple objects could be individually and specifically interacted with. Extending that with more contextual understanding, the avatar could be directed to interact with an object in a specific way. If I'm looking at a coffee cup, could I trigger grabbing that coffee cup in a particular way? That is starting to reduce the scale of the BCI control problem to something very accomplishable with an AI interface and narrow bandwidth of decodable signals. That realization, before I'd even had the opportunity to demonstrate the bidirectional BCI that I built in humans, in the process of building that, I realized that where I wanted to go next was a smart interface between the human and the virtual world that leveraged the BCI. And I called this architecture an AI in the loop BCI architecture, presented that at another conference. And I've used the analogy that instead of having BCI drive a robot, right, where the brain-computer interface is used to have the robotic arm, lift some centimeters vertically in this axis and then move laterally in this axis and then pivot and then initiate a grasp. Instead of all of that control bandwidth, what if, instead of driving a robot, we had the BCI ride a horse, where the horse has a sense of its policy space, its action space, what it can do. The horse has a model of the world that it's interacting with. The horse controls the movement of its own body. It, avoids dirt clods for you. Your control interface as the rider is forward, faster, slower, left, right. It's communicating much higher level control signals in really an extremely reduced bandwidth. In the literal sense of riding a horse, you have reins and you have the tension in your legs to communicate to the horse your positioning and your intent and will as a rider. That is a trivial control surface compared to every piece of information the horse is integrating. I believe I would want to go build that an AI in the loop BCI architecture maximizes the control space of an implanted device to dramatically improve meaningful functional outputs. And I think virtual reality or augmented reality is the environment in which to build this, because you can deliver information to an AI agent or an AI proxy through a virtual reality setting that is actually quite difficult to communicate in the real world, and is a problem that we'll say smart robotics, self-driving cars, things like this are actively solving for us, I feel, the BCI researchers to eventually intersect with. And I would love to keep moving in that direction.
That's absolutely amazing. And I wish you, of course, all possible success to move in that direction and to explore this area more. And I'm sure many people will join your efforts to expand it. Maybe now you can summarize your main results of this study for our listeners.
Totally. So the main results of the VR-BCI work that I completed, both what was submitted to the International BCI Award and what was completed afterwards, are that virtual reality setups are absolutely appropriate, comfortable, and effective in a clinical environment for either work like mine, this BCI development work, or really broad cognitive neuroscience and experimentalist question. It is a robust, profound shift in the ability to run complex experiments. Virtual reality, thumbs up, number one. I would say number two, demonstrated the importance of temporal sequencing in direct brain stimulation to communicate complex information, be it neurohaptic information or other, we'll say, pieces of understandable kind of bits that you want the brain to know directly. And then I would say the bidirectional brain-computer interface work demonstrated kind of a V0 of what's possible in the extended reality hardware that we increasingly have access to as BCI researchers, and suggests the importance of direct brain feedback for learning rates in BCI, and the importance of maybe robust design in leveraging what can be a narrow bandwidth of BCI control signals in a context-dependent, smart, and meaningful way. VR will assist in that design problem, but the real-world translations are pretty immediate.
Yes. And in terms of those new translations that become possible, what became possible that wasn't possible before after you did your study, you completed your project?
Well, I had researchers reach out to let me and the team know that because of the early validation work that we did, their process to bring a VR headset into the clinic, their process of getting their IRB approved dramatically helped. One researcher in particular, frustrated evidently, had been trying to get the kind of approval that I got with my lab to bring in immersive virtual reality years ago, and just ran into hurdle after hurdle because there was a sense that the headsets would be dangerous or uncomfortable for an epilepsy population after brain surgery. The assumptions were that if you'd never been immersed in VR, that the immersion would be awkward and uncomfortable and maybe disorienting. And nobody wanted to put a subject sitting in a hospital bed after brain surgery through any more hassle. The reality is the headsets are extremely well tolerated, and immersion in virtual reality, given the advances that have been made in VR development, is immediate and pleasant. There are things that you can do to make VR uncomfortable if that was the goal of your experiment, but it is not innately that. Helping researchers overcome that kind of bias against VR has been very rewarding, and hopefully made VR research more available and more possible in labs across the states and wherever else IRB style approvals are required. I would say by demonstrating that continuous amplitude modulation was both tolerated and interpreted, I hopefully have encouraged more neurohaptic researchers to explore the extent of dynamic sensory feedback. I have coded but not had time to run experiments that look specifically at modulating that direct cortical stimulation, not in an arbitrary sequence sense, but in a kinodynamic or directly referencing movement and interactions in virtual reality, so that the continuous stimulation reflects ongoing and complex object activity in a real-world-ish virtual recast setting. That ability to connect dynamically direct brain stimulation with meaningful feedback appropriate to a user's choices in interacting with an object much better replicates sensory feedback. To make this a bit more concrete, when you reach out and grab a empty coffee cup, right? You aren't continuously feeling the texture of that coffee cup. You feel something like texture when you run your fingertips over a surface. It's your volitional activity, your movement, paired with meaningful sensory touch that your brain uses to build a concept of texture. We can do that in VR. So I demonstrated the V0, that temporal modulations are innately interpretable by the brain in DCS, in direct cortical stimulation. The next step is connecting that to meaningful human action. I believe at that point, the concept of texture is real, not synthetic. It's actually how texture would be delivered to the brain. The ability from that point to really explore neurohaptics in a functional kind of interpretation of the world, to make neural prosthetics or virtual reality immersion real in the matrix sense, I think is at hand. And the demonstration of neurohaptics for the first time in VR or an extended reality interface, plus the demonstration of temporal integration, I think was the first step in that direction. And then finally, connecting in closed loop. There had been BCI researchers who built a virtual reality model of the robotic system that they wanted a BCI user to control, and did do early training work in virtual reality, but then rapidly left virtual reality to work on the actual robotic system. I think maybe believing that something real world would be maybe more useful. I would suggest staying in VR. I would suggest instead of building a third-person robotic interface in virtual reality, harness the first-person ability. I think there's an opportunity for brain-computer interface researchers to really focus on the interface. Robotics, smart robotics for that AI in the loop architecture will meet us when we have the interface ready. I also feel that first-person neural prosthetics, that's its own brilliant area of research as well, that will also meet us. Our job is this interface with the brain. And I think VR gives us a tool to move faster, to build that interface more presciently as these other technological areas come to meet us. I would also say that closed loop bidirectional system demonstrated that even even something as you would think understandable as a neural click benefited greatly from direct neural feedback as a success and reward signal for the brain learning how to use the BCI. Potentially, by leveraging VR, that ability to design training simulations with direct brain stimulation as feedback to speed up the learning rate could be explored. The training timeline right now for these more complex, high dimensions of control BCI can be months in timeline. I think there is a way, again, leveraging VR, but also specifically tying in this direct brain stimulation as feedback to speed up that learning rate.
Yeah. And now looking into the future, we see already many attempts to create virtual realities where people have their houses and homes and can live there. What opportunity this research, your research, provides for those future virtual communities?
Gosh, great question. I think there is interest in exploring whether humans move bionic, transhuman. The efforts of commercial companies like Neuralink are stated, one, to identify implanted medical therapies, and also to explore human extension and human augmentation. This kind of segues beautifully, Milena, you're great at this, thank you, into that augmentation residency that I'm an advisor to. There is an interest in leveraging augmented reality, virtual reality, brain-computer interface to expand the capacity of the human mind that could be translating human will across distances the body can't reach. Maybe Mars is colonized by robots with human operators well before we ever send a flesh and blood human. Maybe that interface enabled through AR, VR technologies and potentially an implanted interface, is what extends the reach of humans in, I guess, a solar system way. But also that exploration of advancing or maximizing human capability within our own selves. Is there a way to leverage biofeedback, knowing what's going on in our brain and either delivering visual information or direct brain stimulation to maximize some output? That output could be learning, attention, focus, feelings of well-being. There's a lot of work being done now on the use of immersive environments and direct brain stimulation to promote mental health. Virtual reality has a number of applications within psychiatry already, and I'm seeing the field of neuropsychiatry or implant-based therapies in psychiatry absolutely beginning to blossom. I see much in the kind of interface between these two fields, let alone independently. So I think your question of looking forward, where do I see the world, and how does my research, both what I've done and what I would like to go do, interfacing, I think will continue to develop technologies that enhance human life. It's one of the defining features of being human is the complexity of our tools. And I see, AI broadly, it's a bit hand wavy, but software systems which learn to interact autonomously with their world to accomplish some goal, or software systems which use language in a meaningful way to more efficiently interact with humans. Our control surface is no longer, a touch screen and buttons, but the verbal complexity of human language. That's a remarkable improvement. I think augmented realities will give us new ways of interfacing with our day-to-day and each other. Maybe we leverage that for focus. Maybe we leverage that to further kind of divide focus into repetitive multitasking tools. We'll find our way forward there. I think virtual reality gives us a reach and extent to non-local situations, the ability to sit in on a board meeting with people from anywhere in the globe and feel like you're all together around a table, and absolutely imagined places. Like if I wanted at some point, and I think we're moving in that direction, go fly on a Pegasus through a constructed, Greek myth world. Like I see VR being this absolute expansion of real human locality and artificial. Again, I think I've already touched on brain-computer interface, both ability to expand or augment humans extrasensory or outside of any known capacity, alongside the ability to maximize what's already known. I think the future is very, very exciting. And I was fortunate to work in a field that had little bits of input from all of these different spheres: virtual reality, bioengineering, pure electrical engineering, software architecture, interface. Yeah, it was just really fun place to be.
Yes, absolutely. The future looks very exciting after the conversation with you, especially. So you inspire, you really inspire. Now I would like to get back to what we talked at the very beginning of your podcast, the question that motivated you to go through all those stages of your career development and this particular research is the nature of everything and what is a reality. Yes, so what is your current take on that after conducting your project?
Great question. So the lab that I had the opportunity to work in, as I mentioned, the neural systems lab with professors Rajesh Rao and Ojiman and Jeffrey Heron, Dr. Jeffrey Ojiman and Dr. Jeffrey Heron, sat at the interface not only of this kind of neurosurgical brain-computer interface lab, but also a computational neuroscience and AI development lab. So Professor Rajesh Rao is a kind of leading developer in we'll say, Bayesian concepts of consciousness, this idea that one of the fundamental jobs of the brain is to build a prediction of the future, to project a model onto the world around it as a kind of an increase in efficiency. Instead of constantly integrating new sensory information, the brain is filtering new inputs through what it assumes the input is going to be. And so long as that new input isn't terribly different from what the brain is expecting and attending to, then the brain kind of discounts it, right? It might update the model a little bit, but it walks through the world with this buffer of expectation state. I'm influenced by the lab that I was a part of. I think that that's fairly accurate, and that much of reality that we experience, that we consciously identify as reality, is this autonomous kind of consciousness expectation state. We expend great energy when we're newborns and children in building maps of the world, and building almost like a heuristic for how to anticipate that the world will move from moment to moment. The complexity of human interaction is mind-boggling, and yet we kind of figure that one out. And at some point, it even becomes automatic. Hi, good morning. How are you? Fine. Great. Thank you. See you later. Like we build these expectation states to move us through little step of time to each next step of time. And then when life changes greatly or some expectation is violated, expend again sudden great resources to update our model. I think that also explains the importance of meditation, this idea of checking your model, going back to what you're actually feeling and that kind of primary sensation. I think it's a refresh to a model that may have become stale. I think it also leaves you open to properly integrating new experience. I love the role of curiosity in this context and model, because it's that which drives you to challenge what has maybe become unchallenged in a while. And that ability for the human to continue to project new what ifs and new questions into the model to go be tested is, again, maybe characteristically human. So I think, having sat in this bubble of, we'll say, Bayesian concepts of consciousness, I think there's a lot of sense in that approach. I don't think it's the whole story by any means, but I think it's a significant piece. And in that, reality is both the tangible, mappable, mathematically representable reality that physics aspires to understand, even down to the supposedly not mechanistic subatomic reality, which there's a part of me always curious to go back and explore, and this perceptual reality that I walk through my daily life experiencing. And that's fun. I would be curious, again, to go diving back subatomic, but also would love to expand my understanding of the philosophical conclusions of reality. There are people who spent their lives thinking about themselves in the context of this thing, capital R reality, without the scientific tools, without the implanted devices, without the equations or the mathematical capacity, and came to fascinating conclusions in their own right. I would love to see how those integrate with what I have come to see as potentially the way things are.
Thank you so much. And I'm very curious to meet with you in some time in the future and to see new insight that you gain through your research, through the things you do on the same questions. I'm sure that this will be developing and, the model will be expanding. Thank you so much for sharing that with us. Courtnie, I'm sure that you needed to learn so much to do this project. So many novelties, so many innovations. Yes, you were integrating. So what were those main skills that you couldn't do this project without?
The main skills that had to be developed were the ability to build a meaningful experiment and to work with humans to accomplish that experiment. And that's non-trivial. I think that's a major part of being in experimental science. Any experimental science is learning how to work with the tools you have to approach your question in such a way that you learn something if the experiment, air quotes, goes right, and you learn something if the experiment goes wrong. One of the challenges is building an experiment where you actually have a sense of your assumptions and confounds before you go in. And I have a great failure story I could run through on that topic. But experimental design, specifically in my context, behavioral human experimental design, the kind of technical skills for the hardware and software development that my project required, very important. I can launch into how I tackled those. I did it both as well as I could and terrifically and efficiently. It got done, but one of the outcomes always of teaching yourself is eventually getting to the point where you realize how you should have done it. That's the nature of things. And then I would say the maybe soft skills, I don't know if that's quite accurate, of how to bite off way more than you can initially chew and yet slowly build your capacity to handle that so that you reach your goals kind of eventually. Like everything is coalescing together. You see a point out in a distance and you begin climbing a hill that doesn't even entirely exist yet. And there's no steps cut into the cliffside. And yet at every step, you either have the tools to make the next step or the next step suddenly appears. I think learning how to walk in the darkness that way, how to conquer a thing that is completely unconquerable when you start out. That's a skill set that's developed as well. Can I tell you my failure story? I think it's wonderful.
Absolutely. Yes. Yes. And how did you turn it around afterwards? Yes.
Of course, on the experimental design side, my very first implementation of the kind of neurohaptic differentiation task, I had 3 objects and they were visually encoded, which means they looked different. So the patient knew I'm picking up object A or B or C. Each one had their own stimulation parameter assigned. And then they each had a target that you had to learn and throw to the target. And it was a fairly complex task. So I had a training setup side that would teach the person the task. And then we would move into the testing side to see if the task could be accomplished just through neurohaptic feedback alone, no visual encoding, no help. And the first time I ran this task, the subject and I went through the training phase and everything was going great. And then we switched to the testing phase. And I realized that accidentally I'd encoded a fatal flaw in this experiment. And that was, we switched to the testing phase and they could pick up an object and they know how it felt. And they couldn't remember which target to throw it at. Accidentally, I hadn't just made a sensory, differentiation task. I'd made a memory task. And it was a major confound to the design. Fortunately, in VR, very quick to fix. I hit pause. I put labels on each of the targets and went back to training. I had the patient label each target and then moved back to testing. So fortunately, it was a great fix, but it was an incredible lesson and total failure. It would have completely ruined the experiment if I didn't have an easy fix in VR, but a total lesson in how to design experiments and how to think about the unintended confounds of your chosen design. That I hadn't built the task I thought I had, I'd made a memory test instead. A great failure and a great moment.
Yeah, thank you so much for sharing that. And what suggestions can you provide for the listeners who are aiming to submit their projects for BCI Award? And maybe for those who are even not aiming because they're afraid or hesitant for one or another reason.
I would say to those who are hesitant, you never make a goal you don't take the shot for. You can never receive a yes if you told yourself no first. So please try and submit. If nothing else, in the process of building your submission packet, you will learn about the project that you built. Very common in every stage of research from what I've seen, where you realize something you hadn't realized when you go to write the paper. And that is almost universal. So go through the process of preparing your work for presentation and distribution. Take every opportunity you can, and this is really a great one. To those who are building their submission packet and wondering perhaps the angle to take, I would emphasize that the International BCI Award wants you to explain how your work impacts the scientific field and we'll say the research community and downstream the medical community, the patients that might someday benefit from what it is that you're exploring and researching, and building that narrative. The scientific impact, but the global and the human impact is a key feature of your submission packet. I would highlight that asterisks and exclamation points.
Thank you so much. And I know we are already behind our usual time, but I want to ask this question. You mentioned at the beginning your augmentation residency. Yes, the things you are doing in addition to doing projects and studying. Can you tell our listeners a little bit about that?
Yes. So if you actually Google augmentation residency, I'm pretty sure it's still the first hit. It is assembled by a student group out of Harvard that is specifically exploring through a combination of hardware development, software development, and really kind of, we'll say, theoretical development, this idea of leveraging current technologies to augment human experience. That could be, again, extending the capacities of an individual or providing them feedback in a way that allows them to maximize themselves. So there is a brain-computer interface, or BCI, component of this augmentation residency, which is a 10-week live-in hackathon-style event. So a space was rented in San Francisco. This group of chosen artists, designers, engineers, programmers have assembled to work for 10 weeks on a variety of projects exploring different themes within human augmentation. The brain-computer interface side I'm an advisor for is exploring both, again, these concepts of neurofeedback, different decision architectures for brain-computer interface to fit within like an app model or kind of a distributable EEG-based BCI framework. And then also connecting neural signals, the at times initially limited ability of the human to control those signals, into a kind of generative AI space to explore this interface between human imagination and modifiable output reality spaces. This is 3 projects of a larger kind of set of extremely innovative, fringe, expansive approaches to AI, augmented reality, virtual reality, neural recording, neuromodulation, BCI. Very interesting group. I believe this is their first year for full funding for this 10-week residency, and I think it will garner a lot of attention with what's produced at the end of this and hopefully continue to grow. It's a brilliant way to get things built, to put motivated people together with dedicated time and resources. And 10 weeks, it's the first residency of its kind that is taking the style of a hackathon and providing this much support and context for that length of time. Very exciting.
That is absolutely exciting, and I would love to have some of the people from that hackathon on our podcast to share this with our
Perfect.
listeners. So,
Absolutely.
yeah, thank you so
Yes,
much.
yes.
Thank you so much, Courtnie. And for those listeners who want to follow your steps, what would be your recommendation?
So, to those who are interested in brain computer interface, I would say, I guess, first and foremost, I'm available and responsive on LinkedIn. So, Courtnie Paschall, my name is spelled unusually. There's not many Pascals. There's no other Courtnie with an IE Paschall that I know of. So Courtnie Paschall on LinkedIn. DM me there. I'm very willing to send you resources and directions and ideas and explore concepts and hopes and opportunities with you. Specifically, if you don't want to reach out, if you're interested in brain computer interface, there are data sets available online that will give you high quality EEG, non-invasive neural signals, or invasive stereo EEG, ECOG, Utah Ray single unit neural activity recorded during labeled behaviors, sometimes even with video of what was happening. I would strongly recommend, if you're interested in BCI, ask any question available within these data sets, like, can I decode left hand motion from right hand motion, and go dive in. You'll get the experience with the neural signal side, experience with asking BCI style questions. And there's a lot within that kind of first architecture that you can tackle on your own. There's many resources online, and that sets you up for the BCI hackathons that happen fairly regularly across the globe. GTech has a spring school, for example, that runs, I think we talked about this recently, but it's a biannual. It's twice a year, isn't it? Biannual, twice a year hackathon. These are fantastic. You're partnered with a group of people that have all assembled to do something for some typically very condensed period of time. You can get an entire project built that might normally take you 3 months, scraping for bits of time here and there, done in a weekend. Hackathons are excellent. And then if you're still interested, there are increasingly commercial avenues for you to go gain experience in the real world setting. Internships are available. Commercial EEG systems are affordable. There's many ways to get involved, but those first two steps, play with the data set, run a tutorial, join a hackathon, I think would be my top recommendations.
Thank you so much, Courtnie. That was such an insightful podcast. Thank you for your time, for all the amazing information and advice you provided to our listeners. So I wish you all possible success in your amazing projects. And I really hope that we will get a chance to meet again on this podcast and learn again from you about the new developments that you are participating in. And as we're ending our podcast, maybe you have something to share with our listeners, any advice you can provide. So,
last thoughts. Milena, thank you. I know that you and I have been in contact regarding this podcast for the past couple months. You are an absolute delight to work with, and I have loved this interface that you've built here. You are easy to talk to and make the challenges of podcasting so straightforward for my side. I'm just very grateful for your skill and generosity.
Thank you so much, Courtnie. Thank you. It was a great, great pleasure. Are you a fearless pioneer in the world of brain-computer interfaces? Do you have an amazing project that's pushing the boundaries of what's possible? Then we want to hear from you. The International BCI Award is one of the biggest and most prestigious awards in the BCI world, and the deadline for submission is September 1st. But don't worry, you don't need a top-notch budget or equipment to be a nominee or a winner. All it takes is a great idea and the determination to make the impossible possible. So, submit your project now at bci-award.com or find a link in our podcast notes and join us on this incredible journey to explore the world of BCIs. And make sure to listen to our upcoming BCI Award Neurocareers podcast series for tips and tricks on creating a successful submission. Who knows? You might be the next nominee or winner of the International BCI Award and proudly showcase your nomination on your resume to impress potential employers and establish a successful career in neurotechnologies. But don't stop there. If you're looking for more guidance on succeeding in neurocareers, book a free consultation with me, your podcast host, Dr. K, at the Institute of Neuro Approaches. So, what are you waiting for? Let's make the impossible possible together.